Hello everyone, my name is Sobhan. In this presentation, I'm going to talk about adversarial Fisher vectors for unsupervised representation learning. So this is the outline of my presentation. First of all, I start with an introduction. Then I go over background where I cover generative adversarial networks in general and an energy-based view of GANs. Then I move to methodology, Fisher information theory background, Gaussian mixture model Fisher vector, and the topic of this paper, adversarial Fisher vector. Then I cover experiments, how to evaluate this adversarial Fisher vector representation, and how we use them to monitor training in GAN and improve training of GANs, which is challenging in practice. Uh, Eventually, I cover conclusion and references. So let's start the introduction. So generative adversarial neural networks, or GANs, at the moment are state-of-the-art generative models. So in general, in a GAN, discriminator and generator compete with each other to solve a min-max game. So as we can see from this figure, this network consists of two parts, a generator and a discriminator. The generator tries to uh, create like images such that it can fool discriminator. So it tries to improve the quality of generated images. On the other hand, the discriminator attempts to understand and distinguish between real and fake images. So the competition between these two networks finally help both of them to improve themselves, um, and this is like a min-max game or a competition between these two sub-networks. So based on the original GAN paper, when this Nash equilibrium is reached, when the training is finished, the discriminator is reduced to a constant function. So this means that this discriminator just is being used for train the generator. Well, and moreover, in traditional GAN, generator model the data density in an implicit manner, while in some cases we need an explicit model of data distribution. So recently it has been shown that training an energy-based model with parameterized variational is also a similar min-max game, similar to the one in GAN. So this is interesting. But although they are similar, there is a like significant advantage of this energy-based view of GAN, and that is unlike traditional GAN formulation. In energy-based model, discriminator itself is an explicit data, the model of data distribution. So authors in this paper show that energy-based model can be trained using a similar min-max formulation as in GANs. Then they employ Fisher score and Fisher information theory, which are calculated based on the derivative of your generative model with respect to its parameter, to evaluate how this discriminator is learning and modeling data distribution. So uh, this normalized Fisher vector and Fisher distance are calculated, as I said, using the derivative of your generative model, where here the generative model that we are thinking of is our discriminator, to estimate similarity between both individual data points and even set of samples, which is not a trivial task in general. Uh, so one may raise a question here. So why should we have a discriminator that model the data distribution? So we already have the generator in a regular GAN, right? So why should even uh, propose energy-based model? So the point is that yes, the generator is modeling data distribution, but let's say we have a theory, which is the Fisher vector theory here, that can take advantage of the power of your generative model as a feature extraction. But as you know, in GAN, in generator, the input is like a noise and the output is image. But we are thinking about a model that can get image and give you a vector. So that's why we need an architecture like discriminator to be a generative model or to model data distribution. So that's why the energy-based model GAN is interesting. And the Fisher vector or Fisher score or Fisher information theory is a theory that can help us that take advantage of this, the fact that the discriminator is modeling data distribution. So in this paper, author named this Fisher scores calculated from the derivative of the discriminator as adversarial Fisher vector. They show that these adversarial Fisher vector are a state of art for unsupervised Fisher extraction and linear classification tasks. So they also show that they are good perceptual metrics, which means that they are like somehow correlate well with human judgments, so they can be used as a good tool for image search, image retrieval, and similar tasks. And finally, they show that they can improve the training of the GAN neural network, which is a difficult task, by monitoring adversarial metrics. So let's start the background part. So in regular generative adversarial neural networks, the weights of generator and discriminator are updated by solving the following min-max problem, where p data is the distribution of data, dx is discriminator, and gx is the generator. So to optimize the above problem in inner loop, the discriminator weights are updated until convergence given g, and in the outer loop, g is updated one step given the discriminator weights. So, but in an energy-based view of GAN, if we assume that the energy-based model define a density function as Pex, which is given in the slide, then the negative log likelihood of this energy-based model is defined as equation 2. If after equation 2, if we use Jensen inequality, we can reach to the second line of equation 2, where Qx is an auxiliary distribution which is called variational distribution, and HQ is its entropy. So if Qx is proportional to exponential negative of the energy of x, this means that Qx is equal to the density function of your energy-based model. So in this case, we can put the discriminator equal to energy of the data, and your auxiliary distribution equal to p of generator. So this, having these things, we can get equation 3 from equation 2, where the problem in this problem the variational lower bound is maximized with respect to pg. The energy model is then updated one step to decrease the negative log likelihood with optimal pg. So this figure shows better what is going on in this new scheme for energy-based model. In this scheme, the generator is first updated such that sampling from pgx approximate the discriminator distribution. Then the discriminator is updated to fit pdx to p data. So this is why the discriminator here is modeling data distribution, which is really important to us. So if we take a look at both equation 1, which is for traditional GAN, and equation 3, which is for energy-based model, then we can see that they look similar, but there are some differences. First of all, the entropy regularization HPG in equation 3 prevents the generator from collapsing, which is a difficulty in training GANs. So, but we should notice that in practice it is difficult to come up with a differentiable approximation of this entropy. So people usually use heuristics like batch normalization. here we should note that the order of optimizing D and G is different, and more importantly, D is a density model of data distribution, which is in contrast to regular GANs. So let's talk about, so far we have an energy based GAN. We can simply use the present like modern methods of uh, training regular GANs to train an energy based model. And so far we know that our discriminator, if we train this network well, our discriminator is modeling data distribution. But how we can take advantage of this fact that our discriminator is modeling data distribution? So people in this paper uh, employed Fisher information theory. So, but before explaining their method and adversarial Fisher vector, let's talk about a little bit about Fisher information theory. So we all know that generative models such as hidden Markov models have a principal way of treating missing information and dealing with variableness sequences. So generative models are powerful. On the other hand, discriminative methods such as SVM uh, can like construct flexible decision boundaries and often result in classification performance superior to the model-based approaches. Right? So these things that I'm mentioning here are like some arguments from the paper titled Exploiting Generative Models in Discriminative Classifiers. So this is an old paper. So authors in this paper argued that there is a gap between generative models and discriminative models. So they mentioned that already there are some kernels, but if we can develop a kernel, there are some kernels for discriminative models, but if we can develop a kernel based on generative models, we can somehow link these two areas to each other. So they proposed an ideal classifier should combine these two complementary approaches. So the source idea of Fisher information theory like was introduced based on these arguments and in the following paper. So the key idea here is to derive a kernel function from a generative probability model in a set of like RBF kernel for that is used for SVM. So defining a kernel function automatically implies assumption about metric relation between the example. Otherwise, we cannot call it a kernel, right? So to capture the generative process in a metric between examples, the authors uh, use the gradient space of the generative model. So the gradient of the log likelihood of your generative model with respect to parameters describes how that parameter contribute to process of generating particular example. So in other words, this gradient space naturally preserve all structural assumptions that the model encodes about the generation process. So this derivative means if we perturb the model parameters, then how the relative position of this new data point would change with respect to parameters which are important because they are encoding the generation process, right? So using this derivative, we convert a vector from a feature space to a vector to the model space of your generative model. So the length of the vector would be equal to number of parameters of your generative model, the length of your Fisher vector. So here I would like to mention a like nice relationship between Fisher vector idea and back of visual word or simple dictionary learning approaches. So before the advent of deep learning, uh, it was not possible to simply come up with a global representation of an image. So people used to employ local descriptors. So for an image, we used to extract some patches, and we were able to use local descriptors to model each patch using a like short local descriptor. So the methods like sift, hug, LBP were working like this. So in that case, for each image, we had set of local descriptors in a set of one global descriptors. So people usually were using method like bag of visual words, which was like applying algorithm like a k-means on patches. Then we create a coding scheme. For example, we take the first patch. If this is in like the second cluster, uh, then we create a zero vector and we put one in the second element of the zero vector. We do this for all patches of that image, and then calculate a histogram or a counting scheme to come up with that global representation. So people realize that if they use this idea of Fisher vector, which is the derivative of your generative model, assuming that the generative model is based on IID multinomial distribution, then the uh, derivative of the log likelihood of this multinomial distribution becomes equivalent to a bag of visual word histogram, uh, and with just a slight difference, which is a constant, which has no effect in discriminative power of this method. So there is a close relationship between the idea of bag of visual words and Fisher vectors. But here, if we just assume multinomial distribution, they become equivalent. If we assume more powerful generative models, then the representational power of Fisher vector become more powerful than uh, like bag of visual word method. So people started working on like more powerful generative model, uh, like Gaussian mixture model. So they calculated the derivative of Gaussian mixture model with respect to parameters, with respect to means, mixing weights, and like variances in covariance matrix. And then they concatenate for each vector, they concatenate all of these derivatives in a line vector to come up with a global representation of this image. So here the length of, for a Gaussian mixture model, the length would be k plus k multiplied by d plus k multiplied by d. The first k is equal to number of the mixing weights. Kd is equal to like number of elements in mean vectors if we assume that the vectors are in d-dimensional space, and the other kd is number of variances. Here we assume that the covariance matrices have diagonal form. So this picture somehow visually show us that there is a connection between Fisher vector theory and bag of visual word concept, and intuitively shows us that the Fisher vector is a generalization of bag of visual word. So for example, consider this new patch. So when you calculate the derivative with respect to parameter, let's say the parameters we consider just means of the cluster centers or Gaussians. So this means that if we change the position of the means with respect to this new data point, then how the relative position of this data point changes with respect to the means. So so it is like it is capturing the relative position with respect to all of the means. But for like bag of visual words, you are using a hard coding scheme. If this is in cluster 2, just put a 2, put a 1 in the second element of that vector. That's it. But here we are capturing the relative position with respect to mean, but also with respect to variances, and even if you have a more powerful generative model with respect to all other parameters. So this is a more general case than bag of visual words. So let's start with adversarial Fisher vector. So in this presentation, I'm going to typically define adversarial Fisher vector and give you some intuition, more intuition about this adversarial Fisher vector. So given a density model p theta x, where theta are the model parameters of your generative model, the Fisher score or Fisher vector for an example is defined as derivative of the log likelihood of your generative model. So this gradient intuitively map an example into a Fisher vector that is a point on the gradient space of the manifold. So intuitively, this gradient can be used to define the direction of the steepest ascent in log likelihood for the example along the manifold. So it is pointing to the place that this model fit better to your data, right? So the Fisher score encode the desired changes of the model parameters to better fit example X. So the authors define the Fisher information as the presented formula, which act as a normalization factor for Fisher score, and these two with each other work to tells us I mean provide us with adversarial Fisher vector. So typically we can like extend this Fisher adversarial Fisher vector to a distance between two sets, and this is like a having the Fisher information, you can define it in a metric space and act this as like treat this as a real distance. So but as I said, basically we need a derivative of your generative models, but here we consider our discriminator as a model that encode data distribution and model data distributions. As I mentioned, the reason for this is because if we can act a discriminator as a generative model, we can fit these images and we can extract adversarial Fisher vectors from this. But this is not the case for the generator in GAN. So essentially we need to calculate derivative of the log likelihood of your generative models. So this gives us equation 4. But as we know, in an energy-based GAN, the generator is updated during the training to match the distribution PG to P theta. So this allows us to approximate the second term in equation 4 by sampling from distribution, which led us to compute Fisher information and Fisher score in an energy-based view of GAN. So here we replace like P theta with Pz, and the like the dx we replace dx with dgz. So we can easily calculate this ux, this Fisher score, based on the given approximations. And finally, the adversarial Fisher vector is calculated based on the calculated Fisher score. So remember that by using Fisher score, we transform data from feature space, where for example the dimensionality is d, to the parameter space of your generative models, where the length of your adversarial Fisher vector would be equal to number of the parameters of your generative model. Besides, in order to make the calculation of this adversarial Fisher vector efficient, we just used that like diagonal part of we approximate I with its diagonal associated version. This is because to reduce the computational complexity of calculating that negative square root. So let's see the results. Here authors compare adversarial Fisher vector with state-of-art unsupervised methods for feature extraction from networks. So as the results show that on CFAR10 and CFAR100, the adversarial Fisher vectors plus augmentation are competitive even with supervised methods. But there is like an obvious practical problem with adversarial Fisher vector. As I said, the adversarial Fisher vector is calculated based on the derivative of your generative model with respect to its parameters. So, for example, for a deep generative model, for a deep GAN, the number of parameters of your discriminator is something like millions of parameters. So the length of your Fisher vector would be millions of parameters. So we should think about this. If you're going to use this algorithm in practice, we should have a very efficient algorithm to remove the redundant features. So like maybe I think the algorithm like PCA, even PCA wouldn't work on such a data, such a gigantic data. It would be like time consuming. But like method like variance thresholding maybe may can be used. But as you can see, the performance as an unsupervised method is really good. It's competitive with supervised method. So as I said, uh, the Fisher adversarial Fisher vector concept can be extended to calculate distance between two sets. So author in this paper use this fact to calculate distance between set of examples. So what are these sets? Here the sets are like different classes after training the GAN. So this picture shows that this discriminator is uh, like providing us with a good Fisher vector or good adversarial Fisher vector such that it can encode distance between classes. For example, sheep and truck are similar, so their adversarial Fisher vectors are similar to each other, right? Or like cat and dog are similar. If you take a look at the image, the adversarial Fisher vector are similar, so they calculate distance between classes or set of images using adversarial Fisher vector in this figure. So this table, uh, it's like sorry. So as you can see in this figure, uh, like uh, adversarial Fisher vector is achieving better result compared with like uh, methods like AlexNet, VGG, like even a stack of k-means uh, uh, for like measuring how these vectors are matching to our visual perception. So this JND score tells us that like it's like a measure of similarity, subjective similarity. So it tells us how this method can be used for these different representations can be used for image retrieval tasks. As you can see, again, adversarial Fisher vector is competitive based on like both GND and two AFC matrices metrics. So as I said, they also used adversarial Fisher vector and Fisher distance to monitor the training during monitor training quality during epochs. So they compared their method with another metrics uh, called inception score. As you can see, first of all, they both look consistent, especially when you increase number of training examples. The Fisher similarity value, which is a similarity between set of examples, two set of examples can be used for calculating similarity between two set of examples. When you increase number of data points, it becomes similar to inception score. So it means that this uh, this metric based on adversarial Fisher vector can be used to monitor the training in GANs and improve training of the GANs. So finally, this figure, as I said, adversarial Fisher vector, as I said, is like aligned with or a visual perception because it encode manifold information of data and the information about the relative position of each data point with respect to parameters of generative model, which are important because they encode information about the generation process. So all of these things tells us that they are good uh, representations, and they are aligned with our visual perception, so they are good for image retrieval task. Here is the visualization of 5 nearest training example of 10 test example. So for like a resonant 18 middle and Fisher vector representation right respectively. So as you can see, the Fisher vector, the retrieved examples for Fisher vector for each row are very similar. So which means that a Fisher vector is a good measure and a good representation for image search task. So uh, in the last section, I'm going to cover conclusion. So authors in this paper showed that an energy-based model can be trained using a similar min-max formulation as in regular GANs. But there was a very important difference that in EBM GAN, the discriminator was able to explicitly model data distribution. Authors in this paper employed Fisher score and Fisher information theory, which are calculated based on derivative of your generative model with respect to parameter, to evaluate the power of discriminator in modeling data distribution, and also to extract some representation from this discriminator which are more powerful than regular feature extraction. So they showed that they are a state of art, they have a state of art performance for unsupervised feature extraction and linear classification. They are a good perceptual metric that correlates well with human judgment, so they can be used for image search, and they use that to improve and monitor uh, training of the GAN similar to the inception score. So thank you so much for listening.